store the items on a stack. So let's take a look at that. This alternative of choosing between link structures and arrays is fundamental, and it's going to come up again and again when we consider more complicated data structures and algorithms. So we want to be sure to analyze it in the simple case for stacks to set the stage for more complicated applications later on. All right, so to use an array, we just keep the n items on the stack in the array, and the array location with index n is the place, the top of the stack, where the next item is going to go. So to push, we just add a new item at s of n, and to pop, we remove the item that's at s of n minus 1 and decrement n. Now there's a fundamental defect in using an array, and that is that you have to declare the size of the array ahead of time, and so the stack has a certain capacity. And if there's more items on the stack than the capacity, we have to deal with that problem. And that's a fundamental problem that we have to deal with in array implementations in all sorts of algorithms and data structures. So again, considering it for this simple case will pay off later on. All right, so here's the full implementation of stack for using an array to represent the stack. So now we have an instance variable, which is an array of strings, and our variable n, which is both the size of the stack and the index of the next open position on the stack. This one has a constructor, and the constructor creates the array. Now, we're cheating in this implementation to keep it simple, and we'll take care of this cheat in a little while, by requiring the client to provide the capacity of the stack. In a few applications, this might be fine, but in many, many applications, that's too onerous a requirement. The client really can't know how big the stack is. The client might have a lot of stacks that need to be maintained simultaneously, and maybe they reach their maximum capacities at different times, and various other things. So we need to remove this cheat, and we will. But the code is nearly trivial if we have the capacity. To check if it's empty, we check if n is 0. To push an item, we use n to index into the array, put the item there, and then increment n. That's the shortcut in many programming languages nowadays for use the index and then increment it. And to pop, we decrement the index and then use it to return the item in the array. So each of the operations is a one-liner. And this is a fine implementation for some clients. That's array implementations of stack, but it breaks the API by requiring the client to provide the capacity. So what are we going to do about that? Well, there are a couple of things that we didn't consider. We didn't put in code to throw an exception if the client pops from an empty stack. Probably should do that. And for overflow, what happens when the client does too much? Well, we're going to talk about an approach called resizing that will allow us to avoid overflow for clients. There's another issue about whether clients can insert null items into the data structure. In this case, we do allow the client to insert null items, but we do have to worry about, in Java, about a problem called loitering, and that is the idea that we have references to an object in our array implementation in the stack array when we're not really using it. So when we decrement that value n, there's still a pointer to the thing that we took off the stack in that array, even though we know we're not using it. The Java system doesn't know that. So to avoid that and really allow most efficient use of memory, it's best to set that removed item entry to null, so there's no reference to the old item left there, and then the garbage collector can reclaim the memory since there's no outstanding references. So that's a detail, but an important one that we have to take care of in our implementations to make sure that we're getting most efficient use of memory. array access is taken as you of stacks had a defect where we required clients. Okay, our basic array implementation of stacks had a defect where we required clients to provide the maximum capacity of the stack ahead of time. Now we're going to look at a technique for resolving that problem. How do we're not implementing the API. The API says we should just be able to create a stack and it should be able to grow and shrink to any size. So how are we going to grow and shrink the array? Well, first thing you might think of is when the client pushes a new item onto the stack, increase the size of the array by 1, and when pops, decrease the size of the array by 1. That's easy to code up, but not worth it because it's much too expensive to do that. The reason is that you have to create a new array, size 1 bigger, and copy all the items to that new array. So inserting the first n items would take time proportional. If the stack's of size n-1, it's going to take time n-2 time n-1. So first n items would take the sum of the first n integers, which we know is about n squared over 2. Quadratic time to insert n items into a stack, that kind of performance is unacceptable for large problems as we've seen, as we will see many times. So the challenge is to do the resizing, but somehow ensure that it happens infrequently. So the well-known technique for doing that, called repeated doubling, is to, when the array fills up, create a new array of twice the size and copy all the items over. Then we don't create new arrays all that often. So here's an implementation of that. We start with an array of size 1. If we have a full stack, which we know by testing n, which is the number of items in the stack, versus the array length, then we just resize the array into one of twice the length before inserting the item. And how do we resize to a new capacity? We create a new array of that capacity and just go ahead and copy our current stack into the first half of that, and then return it. And that will reset our instance variable, which is our stack, to this new bigger array. So the idea and the consequence of this is if you insert n items into an array, into a stack with this array representation, the time will be proportional to n, not n squared. And the reason is that you only create a new array every time it doubles. But by the time that it doubles, you've inserted that many items into the stack. So on average, it's like adding one operation to cost of 1 to each operation. So if you just calculate the cost of inserting the first n items, you're going to have, instead of the sum of the integers from 1 to n, you're going to have the sum of the powers of 2 from 1 to n, and that'll give a total cost of about 3n. So that's array accesses. So for the copy, there's 2 array accesses. So to insert n items, it's about 3 array accesses. This plot is another way of looking at it, which is the number of array accesses taken as you implement push operations. Every time you hit a power of 2, you take that many array accesses, but in a sense, you've already paid for them by putting those items on the stack. So that's called amortized analysis, where we consider the total cost averaged over all operations. And this is a fine example and useful example of amortized analysis to get efficiency in a stack implementation. Now, what about the pop? We have to think about how to shrink the array. So you might think, well, we doubled it when it was full. Why don't we cut it in half when it gets to be half full? We don't want the array to get too empty. Well, that one doesn't exactly work because of a phenomenon called thrashing. If the client happens to do push, pop, alternating when the array is full, then it's going to be doubling, halving, creating new arrays on every operation, take time proportional to n for every operation, and therefore quadratic time for everything. So I don't want to do that. The efficient solution is to wait until the array gets 1/4 full before you have it, and that's very easy to implement. We just test if the array is 1/4 full. If it is, we resize it to half full, and so then at that point it's half full, and it can either grow by adding stuff or shrink by subtracting stuff, but there won't be another resizing array operation until it either gets totally full or half again full. So the invariant of that is that the array is always between 25% and 100% full, number one, and number two, that every time you resize, you've already paid for it in an amortized sense by inserting, pushing or popping. So here's just what happens to the array for our small client example. And you can see at the beginning it doubles from 1 to 2 to 4, but once it gets to 4, it stays, once it gets to 8, it stays at that size for a while, even though there's some operations. And it doesn't shrink back to 4 until after there's only 2 items in there, and then it shrinks and so forth. So array resizing doesn't happen that often, but it's a very effective way of implementing the stack API with an array where the client does not have to provide this maximum capacity of the stack, but still we're guaranteed that the amount of memory that we use is always only a constant multiple of the number of items actually on the stack. So the analysis now says that the average running time per operation for whatever the sequence of operations is, the average running time is going to be proportional to a constant. Now, there is a worst case, that is at the point when the stack doubles, it takes time proportional to n. So it's not quite as good performance as we might like, but it's what the advantage that we get is very fast pushes and pops, just access array and increment it, and very efficient for most operations. And for many, many clients, that's an effective trade-off to make. So what about memory usage? Well, this is the analysis of memory usage for stacks, and it's actually less memory than for strings. The amount used is between 8n and 32n, depending on how full the array is, and just a quick analysis of the amount of space that arrays take in Java. So again, this analysis is just for the stack itself, not for the strings, which the client owns. So what are the trade-offs between using a resizing array versus a linked list? Those are two different implementations of the same API, and the client can use them interchangeably. Which one is better? In many situations, we're going to have multiple implementations of APIs, and depending on properties of the client program, we're going to have to choose which one is the better one to use. So for linked lists, every operation takes constant time in the worst case. That's a guarantee, but we have to use a little extra time and space to deal with the links. So it's going to be slower. Resizing array implementation, we have a good amortized time, so total averaged over the whole process is good. We have less wasted space and probably faster implementation of each operation. And so for some clients, maybe that makes a difference. Perhaps you wouldn't want to use a resizing array implementation at the moment that your plane's coming in for a landing. You wouldn't want it to all of a sudden not implement some operation quickly. If you need that kind of, or maybe in an internet switch where packets are coming through at a great rate, you wouldn't want to be in a situation where you're missing some data because something got slow all of a sudden. So that's a trade-off that the client can make. If I want that guarantee, if I want to be sure that every operation is going to be fast, I'll use a linked list. And if I don't need that guarantee, if I'm just care about the total amount of time, I'll probably use the resizing array because the total will be much less because individual operations are fast. So even with these simple data structures, we have really important trade-offs that actually make a difference in lots of practical situations. Okay, next we'll briefly consider queue implementations using the same basic underlying data structures. So here's the corresponding API for queue of strings. Actually, it's the same API as for stacks, just the names are different. Instead of push, we have enqueue. Instead of pop, we have dequeue. And the semantics is different. For enqueue, we add an item, say, at the end of the queue, and for dequeue, we remove an item from the beginning. It's as if you're waiting in line to buy a ticket. When you enqueue, you go at the end, and when the one that's been in there the longest is the one that comes off. So let's look at how we implement those, first using linked lists and then arrays. So now our representation of a queue with a linked list, we need to maintain two pointers, references, one to the first item in the list and the other to the last item in the list. When we insert, we're going to add the item at the end of the list instead of at the beginning, and when we remove, we'll do the same, we'll take it off the front. So here's the implementation of dequeue. It's identical to the code for pop for a stack. We save away the item, we delete the first node by advancing the reference, and then we return the item. So identical. To add a node, or enqueue, add a new node to a linked list, we want to put it at the end, so that'll be the last one returned. To add it at the end, so first thing we need to do is save a link to the last node. We're going to need that because we need to change its reference from null to point to the new node. Then we'll create a new node for the end of the list. We'll populate its fields, and then that old link will change that from null to a pointer to the new node. So again, just a few lines of code. That's basic linked list processing. Actually, years ago when we taught courses in algorithms and data structures, much of the course would be about this kind of pointer manipulation. But nowadays, that's restricted to just a few implementations like stack and queue and a few other fundamental data structures. So we don't need so much anymore general programs for manipulating linked lists. We encapsulate them in basic data types like these. All right, so let's go back to our full implementation. And this is just taking care of collecting the code from the previous slides, but also taking care of special cases when the queue is empty to make sure that if the queue is empty after we remove an item, we have to set last to null, make sure that both first and last always are what we want them to be. So those are details that are easy to check. Okay, what about arrays? Well, we won't do the details, but it's not difficult to implement queues with resizing arrays as well. Not difficult, but definitely a tricky programming exercise that people are welcome to try. So we'll maintain 2 pointers, the first item in the queue and the tail, which is the position for the next item to appear. So for enqueue, you add a new item at tail, and for dequeue, you remove an item for head. And the trick is that once you get past the capacity, you have to reset back to 0. So that's a little extra code. And then you have to add the resizing capability as well to implement the data structure the same as for stack. And we'll leave that as an exercise. Next, we're going to consider addressing another fundamental defect in the implementations we've considered so far, that those implementations are only good for strings. What if we want to have queues and stacks of other types of data? And that brings us to the topic of generics. All right, so we implemented stack of strings, but in applications, we have all different types of data that we might want to implement, like a stack of ints, say, or URLs, or cars, or vans, or whatever data that we might be processing. So how are we going to implement stacks and queues for that types of data? Well, first thing that we might consider, and actually we're forced to consider this one in lots of programming environments, is to implement a separate stack class for each type of data that we're using. That really seems unsatisfactory. We have our carefully crafted code that does array resizing and so forth, and we're going to copy that code and change the data type string to the data type van or int everywhere. And what if we have hundreds of different types of data that we're processing? We're going to have hundreds of different implementations. Unfortunately, that situation at the beginning of Java, we were stuck with that, and there are plenty of programming languages where basically we're stuck with that. So what we want to look at is a modern approach to avoiding having multiple implementations for each type of data. So a quick hack that is widely used is to use casting to implement to reuse the code for different data types. So we make our implementation with type object. So everything in Java is a subtype of object. And then the client, when the client comes to use it, will simply cast the result to the corresponding type. I don't want to spend a lot of time on this because I think this is an unsatisfactory solution. So in this example, we have two types, we have two stacks, one of apples and one of oranges, and then it's up to the client when it pops something off the apple stack to cast it to apple to keep the type checking system happy. The problem with this is that the client code has to do this casting, and it's kind of an insidious bug if it doesn't quite get it. So the third attempt that we're going to talk about uses generics. And that way, the client code doesn't do casting. We can discover mistakes in type mismatches at compile time instead of at runtime. So in this case, we put, with generics, we can have a type parameter on our class. And that's inside angle brackets in this code. And then we can if we have a stack of apples and we try to push an orange onto a stack of apples, then we're going to get a compile time error because that stack was declared to only consist of apples. And just the guiding principle in good modular programming is that we should welcome compile time errors and avoid runtime errors. Because if we can detect an error at compile time, then we can ship our product or deploy our implementation of an API and have some confidence that it's going to work for any client. Whereas if the error is not going to get discovered until runtime, it might occur with some client development years after we have deployed our software and be extremely difficult on everyone. Okay, so actually, with a good generic implementation, it's not difficult to simply take every place that we use string and replace it with a generic type name, as in this code here. On the left is our implementation of a stack of strings using linked. On the right is a generic implementation. So every place that we use string type on the left, we use the word item on the right, and at the top, in the class declaration, we declare in angle brackets that item is the generic type that we're going to use. The implementation could hardly be more straightforward, and it's an excellent way to solve the problem of handling multiple types of data with one implementation. With arrays, it doesn't quite work, and again, all programming languages, or many programming languages nowadays have difficulties with this, and Java's got a particular difficulty. So what we would like to do is just declare a new array using our generic type name item, as in the highlighted line here. Otherwise, it's the same. Unfortunately, Java does not allow generic array creation. So there's various technical reasons for that, and you can read extensive debates about this on the web. That's going to go beyond our scope. For now, what we need to do is put a cast in to make this work. So we create an array of objects, and then we cast it down to an array of items. Now, in my view, good code has 0 casts. So we want to avoid casts as much as possible because it really is declaring some kind of weakness in what we're doing. But in this case, we have to put in this one cast. And so we'll refer to that as the ugly cast. It doesn't make you feel good about the code. It's not something that you'd come up with on your own. And that's an undesirable feature, I think, for code so simple as this. But fortunately, we can get through pretty much everything that we're going to do in this course with just knowing about this one ugly cast. So now when we compile this program, we get a warning message from Java that says that we're using unchecked or unsafe operations, and we should recompile with -xlent equals unchecked for details. So we can go ahead and do that, and it says that you have put in your code an unchecked cast, and we're warning you about that because you shouldn't be putting in unchecked casts. And okay, that's fine, and you're going to see that when you do compiles using code like this. I think maybe they might have added to this warning statement, we apologize for making you do this. It's not our fault that we had to do that. We had to do that because of your requirement about not allowing us to declare generic arrays. So with that note, please don't think there's something wrong with your code if you follow our perspective and get this warning message. Okay, that's one other detail that Java takes care of, and that's what about primitive types. The generic type that we're using is for objects, and we're casting down from an array of objects. In order to handle generic types, we have to use Java's wrapper object types. Integer with a capital I is wrapper type for int, and so forth. Many of you are probably familiar with that. And there's a process called auto-boxing, which automatically casts between primitive types and wrappers. So all of that handles the problem of dealing with primitive types kind of behind the scenes. And the bottom line is that we can articulate an API for generic stacks that works for any type of data, and we've got two implementations, linked lists and arrays, that perform very well for any type of data using the resizing or linked lists as we've described. Okay, there's another facility that Java provides that leads to very elegant and compact client code that's definitely worthwhile to add to our basic data. We iterate through the types, and that's iteration. That's what we're going to talk about now. So what we want to do is to allow the client to iterate through the items in the collection. But we don't want the client to know whether we're using an array or a linked list or whatever internal representation we might have in mind. It's not relevant to the client. In a lot of clients, all they want to do is just iterate through the stuff in the collection. Java does provide a nice solution to this called iteration. So what we're going to do is look at how to make our stack and queue and other data structures that we consider later on implement the so-called iterable interface. And it'll work for client code no matter which implementation we use. So let's take a look at the details of that. So what's an iterable? In Java lingo, what an iterable is, it's a class that has a method that returns an iterator. And so what's an iterator? Well, an iterator is a class that has methods has next and next. The Java also allows remove. We think that one is bad news, so we don't use it. It can lead to insidious debugging problems. So has next and next. And so to make a data structure iterable, we're going to implement those things. And it seems like a lot of baggage to carry around. And the reason that we do it, why we go to the trouble of doing it, is that we can, if we have a data structure that's iterable, we can use a very compact and elegant client code in Java, the so-called for each statement. So if we have a stack, we can say for string s colon stack, it means for each string in the stack, print it out. And if we didn't have that, we would, if we're using iterators, we could go ahead and write this longhand code, but nobody would ever do that because it's equivalent to the shorthand. Or we might have to write client code that does a lot of unnecessary pushes and pops just to do this iteration. So that's the key, is to be able to have client code that is so compact for iterating through items in the data structure. So we're going to provide iteration for all our basic data structures. And it's not too hard to do, definitely worthwhile the effort. So here's what it looks like for linked lists. It's got to implement iterable. So what does that mean, implement iterable? It's got to have a method iterator that returns an iterator. What's an iterator? So we're going to use an iter class. In this case, we'll call it list iterator that implements iterator, and it's generic. And basically what this thing has to do is implement these methods has, next, and next. And the semantics is clear from the names. Has, next is supposed to, if we're done, it's supposed to return false. If we're not done, it's supposed to return true. And the next is supposed to give the next item in the iteration. So if the thing is a linked list, we're going to start out at first. That's our first item in the list. And we're going to maintain an instance variable current inside this iterator, which is the current thing that we're iterating. So to get the next one, just like when we remove the first, we pull out the current item and then advance the current reference and return item, moving current to the next place. The client is always going to be testing has next, as I showed in that stub code before. And so when it gets to null, it'll return false and the iteration will stop. But for our iteration, we just have to worry about implementing next and has next, and perhaps using a local instance variable to get it done. We have to probably, to make bulletproof code, throw exceptions if a client tries to call next with no items there, or tries to call remove at all. We're not going to support remove. And for array, it's even simpler. Now with the iterator, we have control over which order we go through the items, and so that's going to go along with the semantics of the data structure. So probably in a stack, you want to get the things in stack order, like the order that come out of the stack, so that's reverse order in the array. In this case, then, next is just decrement and return the next one, and our instance variable is an index in the array, and then has next is okay as long as that thing is positive. A little Java code to provide this iteration facility, but actually within this framework, not too much to do, and you can see how to implement this for your own data types, and we'll use this paradigm for every basic data type that that involves collections of objects that we'll encounter. All right, and in fact, that leads us to actually, for a lot of clients, it doesn't really matter what order we get the items. Really, often what we're doing is just inserting items into a collection, and then later on iterating through the items that we have. That data structure is called a bag. So let's look at what that API looks like. The order doesn't matter, so all we're going to do is add an item. Maybe we want to know the size, and we want to iterate through all the items in the bag. So this is a simpler, narrower API, but still it expresses an important little collection of operations, and we'll use this one. And we've already seen the implementations. You just take stack and remove the pop or queue and remove the dequeue, and you have a fine implementation of a useful data structure. Okay, those are some basic data structures and implementations, and they seem quite elementary and simple, but actually right away we can get to some very sophisticated applications of these basic concepts, and that's what we're going to consider next. Now, first thing to mention is that often the kinds of data types and data structures that we implement are found in Java libraries, and that's true in many programming environments. So for example, stacks and queues, you can find those words mentioned in the Java libraries, and there's a Java collection library in the so-called list interface, which is displayed here. So Java has a general API for sequences of items, and it's got things like append at the end, remove from the beginning, and so forth. And it uses a resizing array, so many of the principles that we consider. There's also a linked list interface. So why not just use those? Why use our own implementations? The problem is often in such library code is kind of designed by committee phenomenon that more and more operations get added. And the API becomes too broad or bloated. It's not a good idea to have lots and lots of operations in the same API. And we'll see an example in a second of the problem. The real problem is that when you do that, you can't know much about the performance, or you can't assume much about the performance. And so you can kind of immediately arrive at bad performance, even for simple clients. So our best practice that we recommend is so few of these basic data structures that we use, and they're so simple, is to go ahead and use the implementations that we've just discussed for these fundamental data structures. Maybe later on, after an experienced programmer who knows what he or she is doing could use some of these library collections effectively, but inexperienced programmers often have trouble with it. Here's a war story from student programming assignments not that long ago. So we have an assignment where you need to generate random open sites in a percolation system. We have one student who was paying attention to what we're saying and uses an array and can pick the indices into that array at random, check whether they're open, and repeat. So the array is n by n, there's n squared things, and it takes about n squared time, which is actually linear time for this application. But then we have another student who had some Java before coming to us and considered himself an expert and said, well, I'm going to use linked lists because I can use Java's library and I don't have to worry about downloading your stupid code. And so I'll just use that one and pick an index at random and delete. And that program took quadratic time. And poor Kenny, when trying to run his program for the huge instance that we asked, found that it wasn't finishing. And the reason is that the Java linked list implementation takes linear time to find an item with a given index, not constant time like an array. And that's difficult for Kenny to think about and difficult to derive that information from the implementation, so the program is just too slow. And with the Swiss knife implementation with so many operations, it's hard to know whether or not the particular set of operations that your client needs is efficiently implemented. So our insistence in this course is that students should not use a library until we've implemented it in class. At least that's some indication that you understand the performance characteristics. So now let's look at some applications then of stacks. Stacks are really actually fundamental underlying computation because they implement recursion. And so you use stacks often every day. When you go use the back button in a web browser, the places you've been are saved on a stack. Right now, we'll look at two examples. One having to do with compiling from a programming language or interpreting into an actual computation. And then the other one is the PostScript language, which is widely used for printing and publishing. So the way that compilers implement functions is using stacks. When there's a function call, the whole local environment is pushed, and then along with the return address, and then the function return is pop the return address in the local environment. So there's a stack there that contains all that information, and whether the function calls itself or not is not relevant. The stack contains the recursion. In fact, you can always use an explicit stack to make a recursive program non-recursive. So this is so when we have the GCD function computing the greatest common denominator, greatest common denominator of P and Q is greatest common denominator of Q and P mod Q, and it just calls itself until Q gets to be 0. And as this graphic indicates, it just does it by saving the information on a stack. Now, a specific example that really shows this off and also will illustrate the utility of being able to process multiple types of data with the same code is this example is Dijkstra's two-stack algorithm for arithmetic expression evaluation. So the goal is you've got an arithmetic expression. This is just actually like a simple stand-in for a program, and we'll talk about that in a second. But let's say arithmetic expressions where you have operands and operators, and you want to evaluate it. And Dijkstra's algorithm is very simple to express. You process through the expression from left to right. If you see a value, you put it on. You can maintain two stacks, and if you see a value, you put it on the value stack. And if you see an operator, you put it on the operator stack. Left parentheses you ignore, right parenthesis you pop the operator in two values and push the result. Now that's a lot of words. Let's look at a demo. So we start out with empty value stack and operator stack, and we're going to move from left to right. So, and those are the top is summarized the 4 types of things that we could wind up with and what to do. So left parenthesis we ignore. The value we put onto the value stack, so that one goes right onto the value stack. Operator we put onto the operator stack. That plus goes in the operator stack. Left parenthesis ignore. It seems strange to be ignoring parenthesis, and we'll get back to that in a second. Value put on the value stack. Operator put on the operator stack. It doesn't seem like we're doing much except putting stuff on stacks. And now when we come to a right parenthesis, that's when it gets interesting. What it says is to you have the top operator and the top 2 values, and that's what you want to do is apply that operator to those values and put the resulting value that you get back onto the operand stack. So we take off the top 2 things, we do the operation, and then we put the thing that we get onto the value stack. And that's the right parenthesis. So now continuing along, we put a star on, left parenthesis we ignore, 4 on, star, 5 goes to the value stack. Now we got a lot of stuff on the stacks, and we got 3 right parentheses, and that's going to finish up the computation. Take the top 2 items off the stack and the top operator off the operator stack, perform the operation, put the result back on the value stack. Another right parenthesis. Take the top 2 values off, perform the operation, put the value onto the value stack. And finally, the last right parenthesis, take the two operators off the value stack, operands off the value stack, and operator off the operator stack, perform the operation, put the result back on the value stack. And we're at the end of the computation, and that's the result. The value of that arithmetic expression is 101. Okay? Yep. Here's the code that implements Dijkstra's two-stack algorithm. We have two different stacks. The operand stack, the operator stack is string. It could be characters, which is just our operator. Then our value stack is doubles. So that's the same stack code, but with generics, we're using two different types of data. And then simply perform Dijkstra's algorithm. If we have a left parenthesis, we read a new string. If we have a left parenthesis, do nothing. If we have plus or times, push it. If we have a right parenthesis, then go ahead and pop the operator. And if it's plus, add the result of the two values at the top of the value stack, and if it's a star, multiply the two values at the top of the stack, and then push the result. So, and then when you're done, then simply print out the value on the stack, and that's a fine and elegant implementation using stacks for any arithmetic expression, and it's easy to extend that to handle other types of things. So why does this work? Well, when the algorithm encounters an operator, say in the inside with you got parenthesis, operand, operator, operand, parenthesis, it's easy to see that what it's going to do inside there is put the at the top of the stack, whatever it is to put the 2 and 3 on the top of the value stack and the plus on the top of the operand stack. And then when it hits that right parenthesis, it's going to perform the operation, and it's going to proceed then exactly as if the original input were that with the value replaced. So just going from the inside out for every operation enclosed within parentheses like that, it's just repeat the argument. It's exactly as if the original expression were 1 plus 5 times 20, and then again replacing that 1 plus 100, 101. That's why Dijkstra's algorithm works. Actually, fairly easy to understand why it works. And you can go ahead and extend this algorithm to add functions like logs and signs or other operators, and have precedence among operators, have them associate multiple operations and so forth. And actually that's on the road to developing a compiler or a way to translate a program from a programming language to a computation. So Dijkstra's algorithm that uses stack is one way for entering an understanding of the basis of computation. items that are in an array is to Java types that you would expect to involve sort. We refer. Okay, what are the rules that we're going to follow? Well, here, let's start with looking at a typical basic sorting problem. Say a university has student records. And for every student, there's a certain amount of information. Maybe there's a class number, there's a grade, there's a phone number, maybe an address. So we refer to an item as a record, or the information that we're going to sort. But in particular, there's a piece of a record called a key. And what we want to do is put the records into order according to the key. That's the sort problem. Rearrange an array of n items into ascending order according to a defined key, which is part of the item. Now, our goal is to be able to sort any type of data. So let's look at a couple of client programs. First example is to just sort some random real numbers into ascending order. So here's a client that calls our insertion sort method. And all it does is read numbers from standard input, then into an array A, then calls insertion sort, and then prints them out. And you can see on the right that the numbers are printed out in sorted order. This seems like an artificial kind of input, but actually we'll look at an application even in this lecture. And there are many applications where random inputs are a fine model. Here's maybe a more familiar sort client that sorts strings. And in this case, it reads the strings from a file using our read strings method in our in class, which takes a file as argument. So we take the file name as the first command line argument, read in an array of strings from that file separated by blanks, call our insertion sort method again. So insertion.sort is a method that takes an array A as its parameter and it as its first argument, and it rearranges the strings in that array to be in sorted order. So in this case, words3.txt has a certain number of three-letter words, and this client program will result in those three-letter words being rearranged into alphabetical order. Here's another client that we could use our sort program for if we achieve the goal of sorting any type of data. In this one, we're going to sort the file names in a given directory. So again, we use the file class from Java, and we go and use the list files method from that class to get an array that contains all the file names in the given directory. And that's an array with file names in it, and insertion sort takes that array as its first argument, and again sorts them, and then we go ahead and go through them one by one and print them out, and they come out in order of file name. So that's three different clients, three completely different types of data. And the first rule of the game that we have to think about is, how can we make it so that we can implement one sort program that can be used by these three different clients to implement three different types of data? And the way that that happens is a mechanism known as a callback. So that's our basic question. How can sort know how to compare data of all these different types without being given any information about the type of an item's key? And the answer is that we set up a mechanism known as a callback, or a reference to executable code, where the client, by passing an array of objects to the sort function, in Java there's an implicit mechanism that says that any such array of objects is going to have a compare to method. Then the sort function calls back the compare to method associated with the objects in the array whenever it needs to compare two items. There's a lot of different ways to implement callbacks, and that's programming language specific. Different languages have different mechanisms. It's all about the idea of passing functions as arguments to other functions, which is a deep area that gets us into functional programming and thinking all the way back to Turing and Church. For Java, because of the desire to check types at compile time, they use a specific method called an interface. And we'll look at the details of how to implement callbacks with Java interfaces now. It's a little bit of programming language detail, but it's really worthwhile because it allows us to use the sorts that we develop for any type of data in a type-safe manner. So we already looked at some clients. This is the example of the client program that sorts the files in a given directory by file name. So it just calls our sort method with an array of some type of object as first argument. Now, built into Java is the so-called comparable interface. And all the comparable interface is a specification that a data type that implements comparable will have a compare to method. And it's generic. It'll be compared to against a certain type of item. Now, when we implement objects that are to be sorted, we'll implement the comparable method. That's up in the top. Class file implements comparable file. And since sorting is an operation that's used in so many situations, many of the standard Java types that you would expect to involve sorts will implement comparable. And all that means is that that data type has an instance method that will implement the compare to method. It'll compare this object against the object given as argument. And depending on some complicated test, it'll return -1 meaning less, +1 meaning greater, or 0 meaning equal. Now that compare to method is really all that the sort implementation needs. First, it says that it's going to take as argument an array of type comparable. So that means the objects in the array are going to implement the comparable interface, or that they'll have a compare to method. And then the sort code can just use that compare to method invoked on an instance of the object like an entry in the array, and as argument another instance in the object like another entry in the array to test whether the first is less than the second, as in this example. The key point is that the sort implementation has no dependence on the type of data. That's handled by the comparable interface. And a different comparable array will be sorted in the same way. They'll eventually, because of the interface mechanism, be a callback to the actual compare to code that goes with the type of object being sorted. Now, there's a few rules, and they're natural rules, but they're worth talking about and paying attention to, that the compare to method has to implement, and it's so-called a total order. And all that's saying is really that it must be possible to put items in order in a sort. So there's three properties. First one says that if v is less than or equal to w and w is less than or equal to v, then the only way for that to be true is if they're equal. And then there's transitivity. If v is less than w, w is less than x, then v must be less than or equal to x. And totality is that either v is less than or equal to w, or w is less than or equal to v, or both, they're equal. There's plenty of natural total orders in the types of data that we normally want to consider for sort keys, like integers or natural numbers or real numbers, or alphabetical order for strings, chronological order for dates or times, and so forth. The cartoon on the right shows that not all orders are necessarily total orders. So rock, paper, scissors is intransitive. If you know that v is less than w, w is less than v, you don't know that v is less than or equal to v. I'm sorry, v is less than w, w is less than or equal to x, then you don't necessarily know that v is less than or equal to x. All right, so the comparable API, then by convention in Java, we always need to implement compare to such that v.compare to w is a total order. And also by convention, it returns a negative integer if it's less, 0 if it's equal, positive if It's greater. This creating the object given as argument. If the types are incompatible, or if either one is null, compare to should throw an exception. Now, again, many of Java's standard types for numbers and dates and file and so forth implement compare to by convention.
So you want to be a software engineer at Google? Go to algoexpert.io. Pick a question, read the prompt, write some code, run your code, write some more.
Hey everyone. Welcome back, and let's write some more neat code today. So today let's look at word search. This is a pretty good problem and it's definitely very popular. So we're given a grid m by n with a bunch of characters, or you could say it's a board, and we're also given a target word, and we want to look for this word inside of our board, and if we can find the word, we return true. If we can't find the word, then we return false. And so within our grid, the word can be constructed any way, but it has to be either horizontally or vertically neighboring cells. So basically what we're looking for, let's say this is our board, we're looking for a path inside of this board where we can move horizontally, right? We're moving to the right, then we go down, and then we go to the left. So this is our path, and we are looking for a word. So we're looking for a path that can make this word. Down here, you can see in the example, they give us a target word, A, B, C, C, E, D, and that's the word we're looking for. We're looking for a path, and we can find a path with exactly those characters. Therefore, we can return true. Now, the question you're wondering is, how can we figure this out? Is there a really efficient algorithm to solve this problem? The answer is no. There's definitely not a super efficient one. We just are going to go through the brute force solution, and that brute force solution is going to be backtracking. So basically, this problem is actually pretty intuitive, right? How would you solve this problem in real life if you didn't have any code? Well, you'd go brute force, right? Let's start at every single cell. So we'd go through every single cell, right? Let's say this is an E, right? Does our word start with an E? No, it starts with an A. Now we have a C. Does our word start with a C? Nope. Does our word start with a B? Nope. Does our word start with an A? Yes, it does. So now let's look at all the neighbors of A and look for our next destination character. Our next target character is B, right? So let's look down. We don't have a B over here. This is an S. Let's look up. There's nothing up. Left, there's nothing left. Okay, to the right, we have a B. Great. Now the next character we're looking for is a C. Are there any neighboring C's? Not up, right? What about to the left? We can't reuse a character, so we can't reuse this A, but we wouldn't want to use it anyway, but that's just another detail, right? We can't reuse any characters. Down here, there's an F. That's not what we're looking for, but to the right, there's a C, right? Obviously, we can see that, and the next character we're looking for is a second C. You know, we could run through this, but it's mainly just brute force, right? We're going through every single position, looking at every single neighbor to see if it's even possible for us to make this target word. In this case, the answer is obviously yes. We have an E and we have a D. We can finish it up. So in the code, we're going to be doing backtracking. So let me jump into that. Or rather, we're going to be doing recursive backtracking. So we're going to do this recursively, or in other words, we're going to do this with depth first search. So let's dive right into it. So one thing I like to do with these problems is just get the dimensions. So I'm going to get the number of rows and the number of columns. So get the length of the board, we get the number of rows, and get the length of the first row, and we get the number of columns. Also, remember how I said we can't revisit the same character twice within our path? Therefore, we're going to need a variable or a data structure for our path. We're going to use a set to add all the current values from our board or positions in our board that are currently within our path to make sure that we don't revisit the same position twice within our path. But other than that, if you've seen any of my backtracking videos, you know I like to follow a formula, so I'm just going to be going through that right now. So I like to create a nested depth first search function within the root or the regular function, because then we don't have to pass in some of the variables like the board and the word, because this is a nested function. But we are going to have to pass in the position of the board that we're at, so 2 variables, row, column for that. And we're going to have to pass in a third variable, I, which is going to tell us the current character within our target word that we're looking for. So if we ever reach the end of the word, or if I ever equals the last position, so if we ever finish the entire word, therefore we know we found the word, therefore we know we can return true, right? That's the good case. The other case is, what if we go out of bounds, right? Out of bounds of the entire board. What if row is less than 0 or column is less than 0, right? Or what if row is greater than or equal to the number of rows, or if column is greater than or equal to the number of columns? That's also out of bounds. So, or let's consider one more case. What if the character that we're at in our word, so word at position I, is not equal to the character that we're at in our board? So board at position row, column. So if this is the case, if basically we found the wrong character, then we also want to return false. And there's one last condition we have to check. What if the character, or what if the position we're at, row, column, this tuple, what if this row, column position that we're at is inside of our path set? What does that mean? That means we're visiting the same position twice within our path. We know all of these things that I've just listed, all these conditions, are basically invalid. If any of these are true, then we have to return false, because, if we're out of bounds, we return false. If we see the same character twice, we return false. If we see a character that we are not looking for, we also return false.
Chasing that A and want to save time on proofreading? Grammarly makes editing one click simpler.
Okay, but once we're done with that, then we know, okay, we found the character we're looking for, right? So what can we do? We can take our path and add the current position to it. So the current row, column to our path, because we found a character that we need. So now we're going to be continuing our recursive depth first search. And so we're going to be looking for the result of this depth first search. So we're going to run depth first search, right? We're going to run it in all 4 adjacent positions. So what I'm going to do is say row plus 1, leave the column the same, and add 1 to I. We're adding 1 to I because we found the character we are looking for. Now we're going to look for the next character, right? So now I'm just going to basically copy and paste this a few times. So I copy and pasted it 4 times because we're going to look at all 4 of the adjacent positions. So let me just fix this up. So you probably see what I'm doing, but basically I'm saying row plus 1, leave column the same, row minus 1, leave column the same, column plus 1, leave row the same, and column minus 1, leave row the same. So we're looking at all 4 adjacent positions. We're running depth first search on all of them, and if any of them return true, then our result is going to return true. Remember, we only need to find our target word one single time. So if we ever find that word, then we know we can return true. So I'm going to go ahead and return that result, but right before I return that result, I'm going to do a little bit of cleaning up. So I'm going to take our path variable and remove from it the position we just added to the path, because we're no longer visiting that position, right? We're returning from this function call, therefore we don't have to continue to visit that position inside of our path. So this depth first search recursive function is always the main part of the backtracking problems. Once we're done with this function, the only thing left for us to do is actually brute force, go through every single position in our grid and run this depth first search function on it. So that's exactly what I'm going to do for every single position, every single starting position in our board. I'm going to run depth first search, passing in the row column, passing in 0 for the position of I, because we're always starting at the beginning of the word. And if we ever return true, if this depth first search function ever returns true, I can immediately return true from our function exists, right? I can just return true immediately. I don't have to wait. And if we never return true, if this goes through every position in the board and we never return true, then I'm going to have to return false out here, because that means we did not find the word that we were looking for. So this is the entire function actually. You can tell that it's definitely not very efficient, right? We're running through the entire board, right? So what's the time complexity of that? Running through the entire board is going to be n times m, because those are the dimensions of our board, and that's being multiplied by the depth first search function, right? because we're calling that depth first search function every single time for every position in the board. So the question becomes, what's the time complexity of the depth first search function? Well, the call stack of that depth first search function is always going to be the length of the word, right? Because the word can only be so long. We can only go through so many characters for the word. So that's going to be the call stack of it. Remember, we have 4 different branches. We're calling the depth first search 4 different times. So it's really going to be 4 to the power of the length of the word that we are given. So it's going to be something like 4 to the power of n, where n is the length of the word. So you can see this problem is not very efficient. So let's just clean this up. So this is going to be 4 to the power of n roughly, right? So it's not a very efficient solution. This is the rough time complexity of the problem. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll